Well, thanks a lot, Matrix. Many of you know Tyler as know Matrix as Tyler. I know him as Matrix. And same ground rules. If you want to know the story, I think there may be an opportunity this evening. I really do appreciate this opportunity, the invitation from the Hertz Foundation to come and talk. It's appropriate. John Hertz started it was originally an engineering scholarship, undergraduate engineering scholarship, at the heart of the Cold War. So he actually coincidentally announced the scholarship 2 weeks before the Russians launched Sputnik in 1957. And then it was only a couple years after that it was actually converted into the graduate fellowship that it is now. So the foundations of the foundation were during a time of consequence in the Cold War. And we are now, again, living in a time of consequence. So it's a great opportunity, I think, just to explore that. We will eventually talk about ending the world in World War III with thermonuclear war. I have now added, after the biosecurity, I've added another way for the world to end to my list of worries, but I am a pathological optimist, so I hope maybe we'll walk away here with some good ideas about what to do. So for terms of reference, so science, engineering, mathematics. Science, the definitions that I use, science is about going after the truth. Engineering is about solving problems, and mathematics is about proof. So, it's kind of a natural sequence of just as we take observations about the world around us, that science self-corrects itself. So originally, you look out, the world looks pretty flat. That's a decent model, and then eventually we go to a round Earth, and then, it's the center of everything, and then we actually realize the Earth moves. And then we eventually realize that the galaxy is just one of many, and then that the actual universe is expanding, and then that expansion is accelerating, and now there's evidence that maybe the acceleration is non-constant. The point is that science is always seeking truth. Mathematics is proof. So once you prove something, you don't have to correct it like science corrects it. So even when we're reasonably certain, so take something like the twin prime conjecture or the Riemann hypothesis. For all intents and purposes, it's got to be true, right? We have checked it up to numbers that, for any practical purposes, but we still don't know that it's true. So mathematics does not allow that it's true until it's proven. But once you prove it, it's always true. So the Pythagorean theorem, you never have to go and check another triangle to determine whether or not the Pythagorean, it's true. Science, we don't know. It's going to correct itself. Engineering, and the perspective that I'm going to share with you today, is really that from an engineering professor and an engineering perspective. It's okay to be wrong. We just, you should know that you're wrong. We just want an answer that's close enough to go and do something about it. And so engineering is all about solving a problem. And ultimately, the best definition of engineering is the one that I like, is Billy Cohen's. It's from 1986. He wrote a little pamphlet published by the American Society for Engineering Education. It's called The Method. And in there, he describes engineering as the selection and application of appropriate heuristics or models. So it's all about picking a model that's going to give you an answer that's good enough. And so and I actually think that we perceive the world through models. And so as just a very simple demonstration of that, here we are, lovely Colorado day at the Cheyenne Mountain Resort, and there's nothing more real than what you see. But it's very easy to demonstrate that what you actually see in your visual cortex is actually not what you actually see. So there's a mapping of what the visual cortex for the right eye actually sees, and so if we overlay that with the Cheyenne Mountain Resort, it's very easy to demonstrate there's a blind spot, and of course there's these things. So we have this perception of 2 pi steradians, of uniform kind of resolution throughout that, and of course the left eye's got one, and you can put them together, and so you have this field of binocular vision where you get depth perception, and so that's what it'll look like, if we were to map that image across 200 degrees or so. And so if you put it all together, this is what the mental model that we have in our visual cortex that's fused between two different eyes with varying resolution throughout the optical field of view, lots of cones right in the middle of the fovea, and then more, the rods or cones in the middle, rods in the middle with a lower resolution. You actually can't see the stuff out here, even though we can actually perceive it because we're continuously updating this mental model. So this is what we think we see, and this is what we really see. So the point is, just, maybe kind of a silly demonstration, but what we perceive, what we think we know, is ultimately always a mental model. And I think there's value in taking our mental models and putting them on the table because it helps with communicating. It helps, maybe if we have different perspectives on something, it's only because we're using different mental models. And so Preston this morning already talked about Snowball Earth. That's actually intended completely coincidental. I was going to talk about Snowball. So here is a model that of the Earth that I used to use in my thermodynamics class. So the question is, when we introduced the first law of thermodynamics, the balance of energy, there's a certain amount of inbound radiation, solar flux coming from the sun, and some of that is reflected away. So the albedo of the Earth is about 30%. So about 70% of the energy is absorbed, about 30% of it's reflected away back into space. And the question that I would ask on an exam is what percentage of the Earth or the radiation from the sun that's absorbed by the Earth does the Earth then radiate away? Is it 1%? Is it a third? Is it a half? Or is it 100%? And of course, the astute students will recognize that, well, from a balance of energy standpoint, the Earth radiates as much energy as it absorbs. And that's, surprising to somebody like me. This audience, not as surprising because you get the first law of thermodynamics. But from that, you can actually write a very, very simple first-order black body radiation model for the temperature of the Earth. And so, you got Boltzmann's law there over on the right-hand side, and so you can solve for temperature, and you get minus 18 degrees, which is not the temperature of the Earth. And unfortunately, as and Preston kind of pointed this out this morning, at 18 degrees, that's actually below the freezing point of water. And so, the water in the oceans would slowly freeze, or quickly freeze, probably at 18 degrees. And it would take a while for them to freeze to their depth. But that increases the reflectivity of the Earth. And then eventually it would get cold enough for the carbon dioxide to actually freeze and turn to dry ice. And the entire time you're increasing the albedo of the Earth. And as you increase as the temperature drops, the albedo of the Earth increases, and so more and more of the energy is reflected away, and so you can see what the equilibrium temperature is. And that's the entire Snowball Earth hypothesis. Fascinating. We do not live on a snowball Earth. So if that's your mental model, that's not a correct model. Fortunately, we do not live on Snowball Earth. A fascinating paper in Science last September on almost 500 million years, so 485 million years back, so 10% of the age of the 4.6 billion years. And this combined multiple different data sets, geological records, and used, really, it's a good example of, I'll eventually talk about the fourth paradigm of science, of using data fusion methods, machine learning methods, to reconstruct a climate going back 10% of the age of the Earth. And as Preston mentioned, that carbon dioxide, it turns out one of the conclusions that they drew from this model is that carbon dioxide is an incredibly important for the equilibrium, as well as the fact that we were much more often not snowball than snowball. In fact, we were usually much warmer than we currently are in the current climate. So our very simple model here was incorrect. We were missing something, and engineering is all about selecting the appropriate model. And so, so the model we had wasn't good enough, so let's add something. We need to add the atmosphere. Again, it's going to be a very simple model. Let's add just a one-layer atmosphere. And so we can write the atmospheric radiative balance. So this atmosphere has some proportion of ability to absorb, so most of the inbound radiation or the largest percentage is in shortwave radiation. The Earth at its terrestrial temperatures radiates with the Stefan Boltzmann's law, kind of at the peak in the long wave. It turns out that some of the asymmetric molecules like carbon dioxide and water vapor and methane, they So long-wave radiation, electromagnetic radiation, right? Particles that have an asymmetry of charge are going to respond to that. So you actually get, kind of this vibrating, carbon dioxide. So, it's good at absorbing. Good absorbers are also good emitters because a carbon dioxide molecule that's vibrating like that can also release energy in the form of a photon in the long-wave radiation. So it turns out that we can write the, if T is the temperature of the Earth, then we can, calculate the absorptivity of it, how much energy is absorbed from the Earth, and then how much is radiated away. Well, that's the same emissivity parameter, but it's radiated in two directions. You have some of it from our one-layer atmosphere being radiated back down to the surface, and you have some of it being radiated up into space. And so now from this extra element in our model, we can now couple it with the Earth, and of course we can solve that for just the temperature of the Earth. We now have a little bit more complicated model, but still a very, very simple model, single-layer atmosphere. And if you solve for the temperature of the Earth, you get something that's much more pleasant to walk around in 14 degrees centigrade than it is minus 18. And so if we take let's put our albedo back to 30%, bring us back up to minus 18 degrees, and then let's add some absorptivity to our one-layer atmosphere and bring us up to what we have. Now, again, very simple model. This is not one that I would recommend going in and setting policy decisions on what emission levels that we should seek, but we can certainly do a what if from this. And so we can correlate the carbon dioxide concentration with that emissivity parameter. It's pretty straightforward to do, and then compare it to the Keeling curve. And so that's what I've got here in the top graph, and then compare it with kind of the observations that we have going back NASA's observations. We can also take that and look at the different representative concentration pathways, the RCPs that the IPCC has set for different emission levels by 2100. So the 8.5 and the 2.6, those represent different radiative loads. So the 8.5 is 8.5 watts per square meter by 2100, additional loading, radiative loading from further greenhouse gas emissions. And the 2.6 is that low scenario, and that's what keeps us below that 2 degrees of climate change from the original. So again, not a model that I would recommend using for anything except for understanding. And there's value, again, from an engineering standpoint, selecting an appropriate model. If your job is merely to understand and to communicate, then a model like this is extremely useful because there was no calculus. It was merely left-hand side, energy in equals energy out, and a little bit of radiative physics. And that was all that was needed. And so some of you may have some climate deniers in your life. They tend to exist. Again, there's a value in communication. There's value in simple models. There's an increasing amount of research being done in attribution studies. And so here's a great example from the UK. May of 2024, the last couple summers, the UK has been having some heat waves. And so UK did a attribution study of the most recent heat wave. And the neat thing about this is it actually illustrates something later on that I'll talk about. Much of my career in flight test has been spent around decision-making under uncertainty. The B-21, we had the first flight of the B-21 almost 2 years ago. And before that airplane takes off for the first time, somebody's got to make a decision. Is the team ready? Is the airplane ready to go and fly? And that's a decision that you have to make under uncertainty. And it's about weighing risks. And one of the things I've become very fond of, and that we've really started to adopt, is using Bayes factors as a ways of assessing risk. And that's you see that in this UK study. And so what they do is they've got a model that they can run with the boundary conditions, and they ran it 2 different times, and that's what you see in the 2 different curves here. And so the blue curve is with the boundary conditions from 1960 up through 2013. So they just reran the model a bunch of times, and then that's what the representative spread of climate looks like in May. And then taking the conditions that were in May of 2024, they reran the exact same model, so the exact same equations, but with different boundary conditions. and different forcing functions, essentially, from the boundary conditions. And here's what you have. So you can now actually do an attribution by comparing these two different models. Until recently, it was very difficult to say that any particular storm or any particular event was the consequence of climate change. But here you can compare these two different things, and you can actually look at in this case, it's the mean temperature, and you compare, what is the probability ratio of the evidence, in this case, the observed mean temperature under these two different hypotheses. One, what's called the natural state, and one which is the all ensemble state. And that relative risk factor, that likelihood ratio, is the base factor. And so in this case, it was 9.8. So it was 10 times more likely that the May 2024 heat wave in the UK was caused by climate change than not. And of course, they did it for the min temperature and the mean temperature as well. So again, just something that's illustrative. And again, I would not recommend this very, very simple toy model for anything other than communication. But these simple models are extremely powerful. They're powerful for understanding. They're powerful for collaboration across fields. So again, the point of engineering is selecting a model that's complicated enough to give you an answer. And if it captures all the, so if it's, essentially if it's captured the primary eigenvectors, if you will, then you kind of have captured the primary dynamics. It turns out that there is, at least in this country, there is quite a wide opinion on climate change. You don't see this across the world. This is from the Pew Research Center, but certainly in this country, there are very different opinions on how much of a threat climate change is. So again, as a point of actually having meaningful policy considerations, I think there's value in having models that we can put on the table, and let's have a discussion about whether it's the assumptions to the model, the validity of the model, or what, and depersonalize, kind of what has become an increasingly polarized discussion in this country. And unfortunately, the polarization has become increasingly personal. So this is another Pew Research study. The one that I think is particularly troubling to me is this upper right one. This is the percentage of either party that views the other party as immoral in the relative change over the last 8 years. And so that's particularly troubling. And so I'm going to offer you a simple model of effective polarization that demonstrates why this is so troubling. So we're going to model the world as a graph, and we have red nodes and blue nodes. And those nodes are going to be randomly connected, and the nodes are going to have a state or behavior. So there's going to be either an up arrow or a down arrow, and this can be an attitude, this can be a belief, and we'll initially randomly distribute those states for all the nodes across the network. And then what we can do is, for every node, at every step in time, what we'll do is we'll step over and we'll count up the number of connected nodes that share the same belief. So if you're a red node, how many nodes, and you're in the up state, how many nodes share that, and how many nodes that you're connected to that are red are in the other state, and vice versa with the blue. Let's count up, let's sum all the ones that you're connected to that are in the down state or in the up state. And then we'll add up the influence parameters, so we'll just sum all those. We'll take the difference between up state and down state, multiply it by this in-group love parameter, and then we'll take the difference between the upstate and downstate for the opposite node and multiply it by an outgroup hate parameter. And then we'll calculate the next node state for every single node. And if the influence parameter is less than 0 or less than some inertia value, so we'll, this fractional delta, I need a certain amount of influence to move me off of my current state. And if the influence is greater than that, then you'll adopt the other, the one state, or you'll stay the same if you're within this inertia. So again, a very simple model, but we'll run it over and actually I do the example here. So if we take a look at this particular node right here, and we just sum up, that's connected to one red node that's in the down state, and there's 2 blue nodes that it's connected to, or 4 nodes, 4 blue nodes, and 2 are in the upstate, 2 are in the downstate, so those cancel each other out. So in this case, depending on the relative ratio of how much inertia there is, this upstate would go down to the downstate because of that -1 right there. So now what we're going to do is we'll take a population, we'll take a world with 2,500 nodes. We'll give a slight advantage to red in terms of population, so 55% are red, 45% are blue. We are initially going to give everybody a preponderance to be in the upstate. So 85% of these nodes are initially in the up arrow behavior. This could be, let's say, for example, early on in the pandemic, everybody decides to wear a mask. That could be the behavior of this network. And the in-group love parameter will be 0.1. The out-group will be 1.25. So there'll be a slightly more out-group hate than there is in-group love. And then let's run the simulation. And so we just time step through time, and then we watch what we're graphing is the change in behavior, change of the state that you're adopting. So this is essentially polarization. So over time, initially, everybody agreed on this upstate. But because of the slight increase in out-group hate, it drove an initially very popular choice for the non-dominant group to adopt the completely other choice. And so again, a very simple model, but one that's extremely informative when it comes to the increasing kind of demonization that we see in politics. And so this model was adapted from this paper, and they actually go through in a lot more detail, kind of the phase diagram. You can look at the continuous nature of this. They actually then go on to look at discontinued groups of networks and how they interact with each other. The point is that all three of these portions of the phase space drive you to polarization. And it turns out that outgroup hate is with this simple model, that outgroup hate is more influential, is sufficient to drive an effective polarization. So I don't have a solution for you, except we do have a model, at least for understanding a problem. And once you haven't, then you can actually, go to the engineering. Engineering is problem solving. So once you kind of have a concise statement of the problem and a model that you can play with, well, now you can start to actually, derive candidate solutions and go through the iterative engineering process to try to engineer a solution to what we have. So that was chapter 1. Chapter 1 was all about models and the fact that we understand the world through models. And what I'd like to do at the end of each chapter is actually just walk through a couple, again, in the spirit of putting our models on the table and putting our assumptions on the table, putting our axioms on the table. I'll give you my axioms. And so my axiom is that we perceive the world through models. And then whether or not some of them are maybe good enough for conclusions, other ones are perhaps just conjectures, but I do see great value in explicitly stating what our models are. They're extremely helpful for communication, for education, for just basic understanding. And you can always make a simple model more complicated by adding additional factors to it. But if you've captured the salient aspects of it, then you've probably captured all the first order effects, and you can have a fairly decent level of understanding. And we'll come back to that last point right there. I do really believe that eventually, the only world I really want to live in is the one where rational thought ultimately prevails. And I'm pathologically optimistic about that world. And I think we can get there. I think this community can help us get there. All right, so chapter 1 was all about models. It's about climate change. It's about cooking the world slowly. Chapter 2 is about cooking the world very quickly. So the closest that we probably were to nuclear war during the Cold War, many folks will consider is the Cuban Missile Crisis. So if you're not familiar or need a little bit of brush up on your history, in October of 1962, we discovered that the Soviet Union had started that previous summer, so about July of 1962, had started putting medium-range ballistic missiles that were nuclear capable in Cuba. And so the Kennedy administration had choices what to do. Ultimately, we considered airstrikes, we considered an invasion of Cuba. Ultimately, we went the blockade route. Of course, after we, vehemently demanded you shall, in the UN Security Council, you shall remove the missiles, and Khrushchev was like, yeah, whatever. So this was the close, and we were very, very close to nuclear war. There was an incident, it lasted for 13 days, and some of our more senior Hertz fellows will probably remember this. Towards the end of that, there was actually an incident that we only learned about in 2002 when all the classified documents were released about we had dropped test depth charges, warning depth charges close to a Russian submarine as part of the blockade. The submarine surfaced, but it had been loaded with nuclear-tipped torpedoes. And the captain of the ship had the authority to launch the torpedoes. He thought he was at depth, out of radio communication. He thought the war had started. And the ship's captain of that submarine, that Russian submarine, wanted to launch the nuclear-tipped torpedo against the U.S. naval vessels that were in the blockade. It just so happened that the submarine commandant, and he had the authority, but the commandant happened to be on the submarine, and he disagreed. And so ultimately, that torpedo was not launched. But we will very quickly, it turns out the political scientists use models as well. So this is a classic book about the Cuban Missile Crisis, initially published in 1972. But he explicitly lays out different models to explain the Cuban Missile Crisis. And the one that we'll step through is the rational actor model to explain the basis for this. So this is essentially a game theory decision tree type of stepping. So we discover, because of the U-2 flights, that there are medium-range ballistic missiles in Cuba. We have two choices. We can do nothing. We can ignore it, in which case there's no conflict. Or we can choose to do something. In this case, we chose to do the easy thing first, right? Demand that the missiles be removed. Now, we also actually tried to go to Fidel Castro and say, hey, do you really want to be friends with Russia? And that didn't go anywhere. But so now the move is over on Khrushchev's plate. What does he do? He also has the option of doing nothing, or, oh yes, we are sorry, we will take the missiles away. Obviously, that's the best outcome for the U.S., but not a whole lot of advantage to the USSR. And so now the ball's back in our court to see what we do. And so now this is where you actually really come down to kind of the brass tacks of what do we do on this geopolitical stage? And we had options on the table. We could do airstrikes. We could invade Cuba. We could go the naval blockade. Again, we have the option of just kind of walking away. And at that point in time, we had placed missiles in Turkey, and that was part of what the Soviet Union was kind of counter-moving, was saying, well, you take away the missiles from Turkey, and we'll take away the missiles from Cuba. Ultimately, we want the naval blockade as, that's what Kennedy decided. And ultimately, the Soviet Union did remove the missiles. But they didn't have to do that. There was an option that they could have then gone, this is, a decade plus after the Berlin airlift, but they could have gone back and done the exact same thing and blockaded Berlin. And if we had invaded Cuba, they could have counter-moved, because Berlin is in the middle of East Germany. They could have actually encircled it, and they could have gone into Berlin and taken over Berlin. So ultimately, a simple model, and this decision tree approach, here is the mental model that I use for how we actually make decisions under uncertainty. And it actually goes back to a polymath at Cambridge, Frank Ramsey. He unfortunately died very, very young at the age of 26, probably from a bacterial infection that he got from swimming in the River Cam. But just a remarkable, wrote in economics. He was a contemporary of John Maynard Keynes. He was a mathematician, economist. But he lays out this decision theory. And this is extremely useful as you're making decisions about anything. First flight of the B-21, Cuban Missile Crisis, where do you want to go on holiday? So you lay out the possible actions that you could take and what are the outcomes that come from those actions. And then very, very importantly, and this is very key, is you need to assign a probability to every possible outcome. And this is just your judgment and kind of the thought right now on what are probabilities. That probabilities are a relationship, a subjective relationship with the world. They're just our impression of what the world is. And maybe there are no such things as objective probabilities, but that's okay. And then you assign a value for that, and of course you can go through the calculus then of what's the expected value, and then compare that to the option of doing nothing. And ultimately, you're also answering a question of, am I trying to optimize or am I trying to satisfy? And if I'm trying to satisfy, then I'm acceptable with just minimizing risk. And if I'm trying to optimize, then I do this where I'm looking for the maximum benefit. And so it's a very useful thing, and we'll come back to this as well. It's also important, I think, as we're looking and we're talking about making decisions under uncertainty, which is just a fact of life, that we acknowledge that there are different types of uncertainty. So here is another mental model, if you will, of the domains of types of uncertainties. And we can divide them into those uncertainties that are just random variables. The literature refers to this as aleatory uncertainty. And then there's ones where we just don't know. And this is epistemic uncertainty, knowledge uncertainty. And the reason it's important for doing this is because the tools for making decisions under uncertainties and for assessing probabilities depend. So if you walk into a casino, much different because you know the probabilities than if you're talking about, say, the first flight of the B-21 and whether or not this system is ready to go to first flight or whether or not there's something that you don't know about. And when you're dealing with these knowledge uncertainties, it's a good thing to let yourself imagine that there's fatter tails of possibilities in there. So as a good Bayesian, when you're doing your kind of Bayesian update about what you expect the world to do, that you've allowed for more possibilities for things to happen. And a lot of this thinking, if I can recommend a book to you, Sir David Spiegelhalter just came out in March, I believe, February, March this year. It's his second book. He is former president of the Royal Statistical Society and professor emeritus at Cambridge. But these are his recommendations for decision-making under deep uncertainty. So a very useful and informative book. And so the reason I frame all that is because it's not about making decisions about the Cuban Missile Crisis. Those are already done. It's actually about making the geopolitical decisions about where we are right now in the geopolitics of the world. And so we talked about missiles, and it turns out that we are in a very similar geopolitical standpoint vis-a-vis the PRC over Taiwan as we were at the heat of the Cold War. And so Chairman Xi has been very clear and has put the People's Liberation Army on a path to be prepared. So right now, the People's Liberation Army is preparing to invade Taiwan. That's not to say that Chairman Xi has made a decision to invade Taiwan, but the People's Liberation Army is definitely preparing to invade Taiwan. And they have created a very modern military, and I'll show you some pictures of what the order of battle looks like in the Pacific right now, that is capable of doing that. And so, again, we are at this point, and this is a time of consequence, not unlike we were in 1957 when John Hertz announced the establishment of the Hertz Foundation, where we need to successfully navigate this to ensure the peace and prosperity of the world. And so the challenge that the PLA has, if they were to invade Taiwan, is the Taiwan Strait. And so here are some examples of what they're doing. So these are relocatable piers. Each of these are a ferry that can sail independently, and then they get close to the coast. They put down these pylons, and then they connect these Bailey bridges. Because the thing about the western coast of Taiwan is it's very shallow, and there's only a couple of ports, and those ports are very heavily defended. But if you don't need a particular port, if you can just take any beach, and you can get deep water vessels, so you can connect these relocatable piers, lower the Bailey bridges, and now you can bring in some deep water, roll on, roll off. You can very quickly unload anywhere you want on the western coast of Taiwan. The PLA is developing that right now. If we look at capacity, If we compare our shipbuilding capacity with the PRCs, they outnumber, from a gross tonnage standpoint, 220 times. A single state-owned shipyard in 2024 built more tonnage of ships than the U.S. built since the end of World War II. That was a stat that CSIS published about 2 months ago, and when I saw it, I had to fact check it 3 times because it was so unbelievable. A single shipyard in China built more tonnage than the U.S. built since the end of World War II. And they've put a lot of that shipbuilding capacity into developing a very modern Navy. And so this is what the order about. This is not all of the forces that we have, and this also doesn't show all of our allies. That's one of our competitive advantages in the Pacific, is that we have some very good allies. I'll take the Aussies and I'll take the Brits over Chairman Xi's allies. He's got North Korea and he's got Putin and maybe or maybe not Iran on a good day. I will take our allies, far more reliable than Chairman Xi's any day. But there is definitely a numerical difference in the forces that we have and what China has. And so I've got a model for that as well. Frederick Lanchester in World War I was interested. He built a model of attrition warfare. This is aimed warfare, and so a simple set of differential equations. So the attrition of red depends on how many blue there are, and then the lethality of blue. How many, and then likewise. So you got a set of couple differential equations here. You can't write a closed form solution, but you can do separation of variables and then write the characteristic surfaces. And so you get this equation for a hyperbola. And so these are your initial state of blue, initial state of red, and then you've got the lethality parameters. And so you end up with what's known as Lanchester's square law. And so blue will win if and only if KB0, so the initial condition, if this is greater than this, then it puts you on a characteristic curve where blue will eventually outnumber red via attrition warfare. So you can look at phase space, and there's this region where red has a numerical advantage over blue, and blue has a numerical advantage over red. And so let's say that red has a 3-to-1 advantage over blue. If we have equal forces, then obviously red's going to win. If blue has a lethality advantage of 4-to-1, red's still going to win. You need better than a 3-squared advantage to overcome the numerical advantage that red has. And so with a 10-to-1 lethality advantage for blue, then blue will win, although they will lose 2/3 of their forces in doing so. So again, a very, very simple model, but simple models can be very, very informative. So we have a numerical challenge in the Indo-Pacific. And at one point in time, we always realized, that's kind of how we won the Cold War against the big bad Soviets, is we invested in stealth and precision weapons in the 1980s. We were not going to compete with the Soviets on numbers in Western Europe. And so we competed on technology. And so for a period of time, we were able to do that against China. This is a just commissioned Type 054 Bravo frigate. This is not your grandfather's. This is a technologically advanced. This is a stealth frigate. Frigates are specifically designed for anti-submarine warfare, and so we no longer enjoy a technological advantage over China. Much less, we probably don't have a 10-to-1 technological advantage over China. We also have a range problem. Turns out Taiwan's a very long way away, and so again, I've got a model. I'll offer you for that. All the aerospace engineers in the room will recognize the Breguet range equation. You can solve the Breguet range equation. Yeah, Matrix is smiling. You can solve the Breguet range equation for the fuel-to-payload ratio. And then you can look at the ranges that we have to go. So if you were to fly a B-2 from Whiteman Air Force Base all the way into the Pacific where it could deliver a payload, that's 6,000 nautical miles. At 6,000 nautical miles with air-breathing technology, it takes 20 times as much fuel to deliver a pound of payload. And if you look at non-air-breathing propulsion, it's even more significantly bad from a fuel-to-payload ratio. The reason that's important is that lethality parameter is inversely proportional to that fuel-to-payload ratio. So if before we needed a 10-to-1 technological advantage And now, because of the range challenge, so if we go, an average of 5,000 nautical miles, we need a 10-to-1 fuel to payload ratio, so we now need a 100-to-1 technological advantage. We probably don't have that. But again, once you have a model, you now have a way of engineering a solution to understand the problem. So how do you solve a numerical challenge and how do you solve a range challenge? Well, you have a bunch of stuff that doesn't have to go very far. And so as we are doing the force design for how do you define Taiwan, you do kind of what Ukraine has done, is you turn it into a porcupine with a bunch of cheap stuff that you can buy in vast quantities and is fairly lethal. So, and then you also have some capability that can go a long distance, and that's exactly what we're doing with the B-21 and F-47, those programs that we're actively testing at Edwards Air Force Base right now, purely to have a capability to change Chairman Xi's calculus about starting World War III. That's what I see my job as on a daily basis, is trying to change Chairman Xi's calculus about today is not the day to start World War III. All right, so that was chapter 2. And then we'll very quickly go through chapter 3 and then open up to questions. So uncertainty is just a fact of life. And I have really come to appreciate the base factors, and maybe we can talk more about techniques for using those during the case. So very quickly, we'll go through this final chapter. And I love this quote by Bertrand Russell. There is something to be said for intellectual humility. And if you're familiar with the concept, the notion of the fox and the hedgehog, there was a Greek poet that wrote this, but then Isaiah Berlin wrote a very famous essay back in the 50s about the fox and the hedgehog. The fox knows many things, but a hedgehog knows one big thing. And Phil Tetlock, who ran the Good Judgment Project and still runs the Good Judgment Project, wrote a book, Super Forecasters, and he identified those characteristics that make folks very, very good about predicting what the future holds. And they tend to be foxes. They tend to have many different ways of looking at the world, many different models, if you will, of understanding the world. And the exciting thing, and also in this image I put an eagle and a frog. That actually goes to Freeman Dyson wrote an essay in 2009, 2010 about the eagle and the frog, which is very similar to the fox and the hedgehog. But one more model I'll offer you here is this notion. It's not my notion, but this concept of the fourth paradigm of science. So if the first paradigm of science is that empirical observation of the world, observing the world and explaining, it looks like it's flat. No, you look at a lunar eclipse and the edge of the Earth's shadow is round, so maybe the Earth is round, type of thing. So empirical observation over time. Eventually, you have kind of the theoretical aspects. So we had Kepler's laws, based on observations of the planets. And then Newton, when he came up with the universal law of gravitation, he showed in the Principia that if you have an inverse square law, it predicts that planets would go in ellipses. And so, you have this theoretical. So the second paradigm of science is this theoretical thing. And then once we had the ability, and the Navier-Stokes equations, the Maxwell's equations, those are all theoretical things, but it's very difficult to solve any meaningful complex problem in theory with pencil and paper. But once you have computers, then you have this computational ability. So computational fluid dynamics solves the Navier-Stokes equations in a digital environment. And so you have this computational paradigm of science. And then finally, we are now in the 21st century, where we have these very, very large data sets, we have these machine learning tools, we have this data-driven science and data-driven discovery. And it turns out that there are structures, there appear to be structures in many of these data sets that we just as humans, we haven't been smart enough to figure out. And you can do things like, you can actually take a bunch of, let's say that we didn't know about Kepler's laws, or we didn't know about the inverse square law for gravity. You could take a lot of planetary data, and you could feed it to a neural network, and a neural network could tell you that, this is very consistent with a inverse square law for gravity. And so, some examples of that in the realm of protein folding, which we've talked about. So, kind of empirical observations, X-ray diffractions, and then, some theoretical things. And then eventually we had, essentially the finite element analysis applied to proteins, but it still turns out that that's a very, very difficult problem. And of course, we've talked about AlphaFold a couple times, throughout the week here. So I'll do this very quickly, just because it's so much fun. So as we talk about models, this is many of you will probably be familiar with the Lorentz equations, a simplified version of the Rayleigh-Bernard convection that Edward Lorenz studied. Really kind of the first observation of chaos. And it turns out, so if you're not familiar with chaos and sensitive dependence on initial conditions, there we go. So what I'm showing over on the right-hand side is just a perturbation in all three axes by 0.001. So on this scale, that's about a 10 to the minus 6 perturbation. And you start these 2 points, and at 10 seconds, they are completely divergent. So classic sensitive dependence on initial conditions, the definition of chaos. So I am not a machine learner type of person, but I do have scikit-learn, and I can play around with neural networks. And so a very, very naive, simple neural network. I took the Lorenz. I took 6 random trajectories for 4 seconds, which gave us 2,400. Not a big data set whatsoever. But I don't need a big data set because this is a very, very simple neural network. Just a input layer, 2 hidden layers, a total of only 183 parameters, and there's what you get. So again, this is just, to me, this is absolutely mind-boggling that there's now this capability within data of actually understanding kind of structures for things. And this is a feed forward of 5 seconds, and it doesn't get the trajectory anywhere near exactly right. But it's a chaotic system, so I wouldn't expect it to. But it has captured the structure, the fact that there's these 2 attractors in phase space. And it's captured that structure from, that was the first pass. I had no idea what I'm really doing. I'm just feeding data to a neural network. And so, as we're looking at digital engineering and these really large models and these reduced order models, and Kieran Wilcox's group at UT Austin, last night I had dinner with Marcia from UT Austin as well, who's a West Point grad, another Hertz investment. But there's these reduced order models for kind of understanding the world are very useful. And so the final thing that I'll leave you with, if you haven't come across this idea of sparse autoencoding, this is a useful mental model for you as well to have in your toolbox. And this is where kind of our everyday perception, so think our visual cortex of the world, presenting to us a model which isn't really what we see, kind of breaks down. So if we think about vectors in the space that we're familiar with, 2D and 3D, and we take just 10 random vectors, in 2D we can probably encode 2 different things. We have 2 mutually orthogonal directions. In 3D we can encode 3 things. And that's about all the information that we have. And so if we go to higher and higher dimensions, it actually turns out that our intuition from the world that we live in is inaccurate. So here is just randomly selected vectors in a variety. I'm showing the 100-dimensional vector space here. So I just picked 10,000 vectors in a 100-dimensional vector space, just random vectors, and I also am showing 20 dimensions, 10 dimensions, and 2 dimensions, and then taking the dot product between all the pairs of vectors and then plotting a histogram to see, what is the distribution of angles between random vectors. And it turns out that it's really hard to see there, but at 2 dimensions, it turns out that they're pretty much all angles, not surprising. Once you get to 10 dimensions, you start to see a little bit of, and there is a little step in there where I nudged all the vectors. I did a little optimization loop to try to spread them out as much as possible, so it's just a little random variation, and there was a gain factor about how much area is under here. But the point is that when you get to 100 dimensions, and if we zoom in here, so if we relax what we mean by orthogonal to, between friends, it doesn't have to be 90 degrees, doesn't have to be pi over 2. We'll accept 89.5 to 90.5 is orthogonal enough for encoding information. So it turns out that in 100 dimensions, you can effectively encode far more than 100 pieces of information. There's 10,000. So, that's a factor of another 100 pieces of information than would be implied. And so that's kind of the magic behind this 4th paradigm is the fact that there are these structures, potential structures, embedded in the data that we can't perceive, but that there's some of these emerging scientific techniques. And so with that, my final set of options, so to the extent that anything is real, and that's the entire Plato's Cave allegory aspect reference, I do think that this fourth paradigm of science is very, very promising. I also will offer to you that the second law of thermodynamics applies to social systems as well. And to the extent that society is going to work and that we are not going to destroy ourselves or let something else like something that from Mother Nature, a biothreat, that it requires an investment from people that know a thing or two and can inform policy and geopolitics and help make better decisions. And so that's kind of I guess what I'll put out there at this time of consequence to the every bit as consequential as it was in 1958 when the Hertz Foundation offered its very first scholarships, is that it is a time of consequence right now. And I have been deeply, deeply impressed by the level of conversations that I've had over the last couple of days and the level of commitment, from the Hertz Fellows and from the Hertz community. And so I'm actually walking away from this workshop very optimistic about the promise of the future. There are some very big challenges that society faces, but I'm also convinced that with folks like this working on them, that we're probably going to be okay. We do have to prevent World War III, though, and that's probably the thing that I'm most worried about. So, all right, only 10 minutes past what I think I was supposed to do, but we do have 20 minutes for questions, so.
I think they've asked us to introduce ourselves, so I'm Kyle from Stanford. I'm not in the military, but I have a question I'm dying to ask you.
Yes.
Because half my family's from Taiwan. So you know this better than the rest of us, but CSIS put out a white paper of simulated war games over Taiwan based on public information. And I think the surprising conclusion was that in most of those, the US coalition does fairly well, or at least neutrally. I guess you showed this very scary plot of how badly they outgun us and so on. But if I understand from that white paper, it was like how much mass the Chinese amphibious force can land, counterbalancing is how quickly we can target and strike them with anti-ship missiles. Yeah. And if we can just attrit them, then they can't really accomplish their objectives. I'm just curious what you have in an unclassified setting to say about this.
Absolutely, great question. And the invasions are hard. Amphibious invasions are extremely hard. And to prevent the invasion, to stop the invasion, all you have to do is sink enough ships. I did show, so the Lanchester's square law, very, very simple. You can actually make it more applicable. So that was what I would call a first order model. You can actually add stealth to it. So that's aim fire. And so you can add parameters to it that actually simulate salvos and how difficult it is to in decoys and make a more complicated model. And all that plays. I guess what I'll share is, so from open source, we've done lots of war games, and depending on how you play with the assumptions and everything, you can look at, in open source reporting, we're expecting 40, 50, 60,000 casualties on the U.S. side or the Allied side in the first week alone. That PLA rocket force, the PLARF, I think they know where Guam is. And they have the size, the magnitude of the rocket force that they have. Now we also have some anti-missile capabilities. So again, it comes down to that. Probably the most encouraging thing is that what we're really trying to do is actually not win that war, but trying to change Chairman Xi's calculus about the cost. So if we go back to that Ramsey's decision tree, how do we influence Chairman Xi's Ramsey decision calculus? We can do it through the loss side. So we can increase the probability of the loss, and we can increase the magnitude of the loss. And so the capabilities that we're developing are really not because we want to win a war, but because we want to deter the war. And Eisenhower very famously said, the only way to win the next war is not to fight it. And so I am encouraged. It is a difficult challenge for Chairman Xi, and I am, that's part of the reason I'm still wearing this, is because I think we're making a meaningful contribution to having capability that helps change his calculus about today is not the day to actually invade Taiwan and start World War III, to give us time for a diplomatic solution and to move to this kind of, post Second Cold War geopolitical era. I guess the kind of the threat, so the way that we're always worth, again, from a model, what is Chairman Xi's model of the world order? Chairman Xi's model is that this world order that has kept the relative peace and prosperity since the end of World War II was created by the West for the benefit of the West and at the cost of the People's Republic of China. And in his mind, in his mental model, is that the U.S. is trying to contain China. And so when we use language of containment, then that is actually reinforcing the mental model that Chairman Xi has. So again, it's, I tend to think of the world as an engineer and in terms of models, but I think it's useful for understanding somebody else's perspective about how they see it and how can you have a meaningful conversation about moving towards an international world order that benefits everybody that's part of this beautiful planet. We had the blue marble up there. It is a beautiful planet. We should probably keep it.
That was a wonderful talk. Thank you. So I'm curious how you think about, you talked a lot about applying rationality to these conditions in warfare. I think there's a great historical example here, which is, our founder, Edward Teller, was very invested in sort of individual rational decisions, I think you would say, to develop more and more powerful nuclear weapons that on the one hand, I think within a very specific context, you would argue are rational, and yet I don't think any of us would sort of freely, rationally choose a world in which the world could, as you said, very rapidly melt. And so, but it's interesting that we actually have another very powerful tool for solving these kind of game theory problems, which are systems of morality. And, of course, this results in a lot of societal disagreement, but, we have moral systems where if you live in a society where everyone is practicing some degree of nonviolence, that actually results in a society that we would all choose to live in. And so I'm curious how you think about rationally, sort of applying this rational framework to thinking about moral systems, and in particular moral systems that govern how our society engages in warfare, and when we decide that certain acts of warfare are morally justified or not.
Yeah, I love the question, and it's one that I'll have to spend some time thinking about. I would love to have a toy model to be able to put on the table that lets us, kind of tweak the parameters and discuss that, and then oh, that does make sense. And then how do we, to your point, how do we actually move? How do we create the incentive structures? Because the model that economists love to use is incentives. And what are the incentives? Show me the incentives, and they'll show you the choices that people make. And so, if we can, under that model, if we can know the state that we want to go to, and the state that we're at, and also in Billy Cohn's, the method, that's what he defines as, if you've ever tried to take something from what it is and then use the resources available to take it to some future state of what it is, then you are an engineer. He says that in his very opening of that. And so that is actually kind of engineering a society, if you will, a society based on morals and ethics that we all want to be a part of, that will, I guess, more likely ensure, so the base factor of ensuring a future society that we can all live in is probably greater under that. So I don't have a good one, that defines that, but maybe that's a interesting little toy math problem that somebody here will probably have by dinner time, and we'll probably have on the table, and we could discuss it at dinner, as you're hearing Matrix's story about how he got his call sign.
Over here, Molly Schwartz from MIT Lincoln Laboratory. Thank you very much for this talk. I have another question about rationality, and I think you talked us through a very nice model of how we apply a rational actor framework. And I think to first order, that's probably the right framework. To second order, it may not be. And you also walked us through a very nice example of how this sort of in-group, out-group bias, which is fundamentally an irrational bias, leads to very different outcomes. And so how do you as a decision maker and how do we as decision makers think about how to incorporate sort of the human element, the fundamental irrationality of the way that we go through the world into these very consequential decisions?
Oh, geez. I should have, Matrix, you warned me. This is a smart so I think that, I mean, that is the million-dollar question, isn't it? I don't have a good answer. I guess I will fall back on the fact that there is an element of human behavior and human choice that is a random variable. And so there's a stochastic aspect to this. And so, not only do we have to account for, kind of the epistemic uncertainty of, what is Chairman Xi going to do, but what is we should probably leave under that. So one of the things we do in flight test is before we go and fly an airplane for the first time, we think about every possible way that flight could go wrong. And so it's this scenario planning. And then you think, well, what's the likelihood of each of those? And so you need to assign a non-zero probability to all those potential things to leave the possibility that could happen. And then, the part of the base factor that I didn't really go into, but it's a great technique for continuously incorporating new information about the world and adjusting. And that's what those super forecasters do. Is they're like, oh, I think it's a 76% likelihood that interest rates will go up. And then a new piece of news will come in, and they're like, oh, it's now 78.5. And then something else will happen. They're like, oh, no, I'm at 74 now. And so they're continuously adjusting their expectation about the world. We should probably always assign a non-zero probability to that, kind of chaotic random variable that a human is just going to do something really, really stupid. We see it all the time. And then how do we mitigate? What are the so if while you're here you drive up Pikes Peak, you'll see it's a very twisty, turny road, and there's some places where there are drop-offs, and there's a lot more guardrails now than there were when they first constructed the road. And the way that they decided where to put the guardrails is where the cars drove off the road. And so if we can do that scenario planning of those kind of non-rational actors, and like, ooh, you know what, that one has a fairly significant non-zero probability. Maybe we should have a guardrail on that one.
Oh, hi. Hi, my name's Grace. I'm currently a now second-year PhD student at Stanford in the Aeroastro department. Also work a lot in decision-making under uncertainty in the Stanford Intelligence Systems Laboratory. So love your presentation. Made me go oh yes, decision-making uncertainty. Mine's more of I don't know if this is more just a thought / moral kind of question here and there. I think especially since being in the aerospace domain, I know that defense and aerospace is very tightly interlinked. But then I also have kind of seen this narrative quite often within this domain where it's you need to keep developing your own defenses / different weaponry, whatever it be, to kind of make sure that you still have a big stick you're holding behind your back while the other team, I guess whatever it may be, is always there. I'm wondering, can we build a different narrative for the future? Is there a way that we can, rather than building up additional weaponry / different stuff in general, to have within our own defenses? I feel that honestly makes the problem worse in a sense, because now we have all access to all these different tools. I think one of the things that made me really kind of concerned from recently, where I think there was this one UN resolution where they prevented nuclear weapons from not being deployed in space. I think there was
Yes.
that was a huge thing over there. But I think is there a way you think we could try to build a future towards that, where we're not trying to build up defenses all the time, but rather than maybe taking them away, and that actually causes more diplomacy in the future because we don't have access to it anymore?
Yeah, so I love the question. I love the sentiment. And that's the world that I'd love to get on that path personally. As humans, we don't, again, as a Bayesian, as a good practicing Bayesian, we don't have a very good track record For pretty much all of human history, you cannot find a decade when there wasn't a major conflict in human history. Now, that doesn't mean that we can't necessarily change the incentive structures to kind of make that less likely. We had great, in the backup slides, and I won't pull them up in the interest of time, but I've got the nuclear arsenal, and you can look at what it is now compared to the peak of the 1970s at the height where, we had enough nuclear warheads to essentially destroy the world 8 times over. You'd think one time would be enough. But we have made progress since then by kind of changing the incentive structures. The challenge now is actually they're far more proliferated than they were in the 1970s, a lot more countries. So we no longer have the game theory that kind of had its heydays under Edward Teller and the mutually assured destruction and everything. That was a more simple game theory problem to solve because you had 2 actors. And we now have a world where we have many, many different actors. And so that's probably I haven't studied the chaotic dynamics of that particular game problem, but that's probably a much more difficult thing. I do think it's important that we reinforce through international rules and information kind of those norms. For example, no nuclear weapons in space. Russia has recently threatened to put a nuclear weapon in space. It's a big juicy target. The dependence that we have on that space layer. And it wouldn't take but a couple of electromagnetic pulses in space to render everything that's in space useless. It also wouldn't take but a couple of anti-satellite that create a lot of debris that create certain orbital planes completely useless forever, or for at least for forever as far as our lifetime. And so how do we continue to reinforce kind of the norms through international organizations and doing so? So there's 4 instruments of national power. There's diplomacy, there's information, there's military power, and there's economic power. And all 4 of those need to work together. That's another model. But all 4 of those need to work together to reinforce those things. So I'm hopeful. Hope's not a strategy, though, is it?
All right, we're going to take one more question.
General Wickert, I'm Alfred Spector,
Yes, sir.
MIT, and also on the Hertz board. It was a great talk. All of us are modelers in the room, right? I think every one of us is. So you chose a topic that was, perfect for a diverse group like ourselves. Now, if you go back to about 2000, there was a guy named Leo Breiman. I don't know if you know that name. He was a statistician. Some of you may know him from the statistics community. And he looked at the sort of traditional world of statistics, the so-called data modeling culture, where we drop an apple from a tree and do some measurements, and then we come up with a linear model of something or other, and many of the things that you talked about. And he talked about that data modeling culture as dominating statistics and dominating, frankly, most everything, the way we even teach in high school. We teach, to the students that can, we teach calculus, a modeling technology that's the basis of much of what you discussed. But he then introduced the fact that he thought the world was moving to what he referred to as an algorithmic modeling culture. And what he was really saying is there's so much data and so much computation now, machine learning is going to become preeminent. Some people at the time would say it's not even modeling, right? It's muddling, right? We just have all this data, we create a muddle, and yeah, it says something. But now if you look at it, and to give you one of the examples you brought up was sort of the game theory of the Cuban Missile Crisis. In diplomacy, which is a game of strategy, machine learning algorithms, these muddling algorithms, win very effectively, and they win in poker very effectively now. Just as another example, a place where I was head of research at Google, we used sort of a combination of data modeling and algorithmic modeling culture to make Google search work. Traditionally, it's easy to compute a number, it's not secret. More than 100,000 person years of work went into tuning Google search with traditional mechanisms, understanding notions of synonyms and antonyms and attention of what people were trying to. It was all done using the kind of models that you described as we think about seeing a scene. How do we do that? So in your talk, I observed your talk was about 80% of the data modeling culture.
Yeah.
And only the last 10 or 20% was the world of machine learning and the other part. So 2 questions for you. One is, do we need to teach it with a different, do we need to now reverse things, or at least have a hybridization that's more equal as to the modeling culture that we're going to be teaching our cadets at the Air Force Academy and all of ourselves? And second, is the culture of the Air Force moving fast enough that when we have, say, the information fusion of things coming at us from a variety of sources and having to decide what to defend and how to attack and whatever, we need instantaneous decisions that may come more from the algorithmic modeling culture and the speed of machine learning. So 2 questions, education and then deployment.
I love the question, and this is actually something that we have spent quite a bit of time when I was back at the Air Force Academy debating, specifically in the statistics realm. So it turns out that the way we teach statistics is very much, I mean, the way we teach everything is the way that we were taught. And the way that the people that taught us, depending on how old you are, was the way that they were taught. And so it turns out that you could trace it all the way back. The way that we teach calculus is the way that it was invented in the 18th century. And it turns out the world has changed. So if we take statistics, for example, we still teach to math majors this family of distributions. Here's where chi-squared is applicable, and here's this test, and here's this test, and here's this distribution. And it turns out some of those distributions do match the real world under certain sets of assumptions, and some are poor fits, but you still use them anyway. And the way that statistics are often practiced is, in the modern era, is all bootstrapping. It's like, I don't care what distribution, I'm just going to resample the data, bootstrap it, I'm going to get my distribution, and then I can actually use that to do a relative risk ratio between 2 different assumptions. And so why do we still teach things if that's not the way they're going to practice? But then it comes down to this pedagogical question about, well, how do we actually acquire knowledge and how do we learn things? And sometimes it's difficult to learn kind of the modern things if you don't have the fundamental underlying baseline. So as another example, at the test pilot school right now, which is out at Edwards Air Force Base, we just went through a very healthy debate as part of a curriculum review about how should we teach future testers? And should we teach them, it is a lot of our systems now are data fusion. It's kind of how that science paper on the 485 million year history paleoclimate paper was done. It was fusing multiple different data sets together. And a lot of the systems we test are fusion systems. And so there's this data-driven kind of test that we need to equip our next generation of testers with. But you should also kind of understand the basic aircraft dynamics in classic flight test about, okay, when I push on the stick, the houses get bigger. When I pull back on the stick, the houses get smaller. And how quickly they get bigger and that kind of, pencil and paper, the things that Chuck Yeager did, and the ability to kind of understand, because those are very simple models. And so as with anything, I think the answer is probably not either extreme. It's probably a hybrid, a mixture of the both. And I think you start with some of the underlying theory to have these simple things, but you explain that, hey, there's this richer world and there's this other world, and we're going to get to that too. And so from a pedagogical standpoint, that's how we do it. Very quickly on the second question about, kind of the real-time decision-making, this is also a very ripe topic, within the folks that are thinking about the future of warfare and what is that like. And, and there's implications in terms of autonomous weapon systems and how much authority and where's the human on the loop, in the loop? Are they part of the loop? Do you just completely turn it over to the machines? I don't think any of us want to live in that world. And that fully autonomous warfare, there's plenty of, that's the basis for so many different science fiction movies and stories. But it turns out that if there's certainly an incentive for the other side to adopt autonomous reinforcement of human decision-making because you can make decisions far more quicker. You can make the sense-making aspect of it is so much more rapid. And there's this concept of the OODA loop that many of you may be familiar with. It came from John Boyd. It's the observe, orient, decide, act. And if you can operate inside your enemy's OODA loop, then you can make decisions quicker and you will defeat them. And Sun Tzu has a lot to say about that as well. And so I think probably that's really where we need on a decision calculus side standpoint. But that means that we need to also educate our future military leaders and decision makers to understand kind of how do these systems work. And that's where, there's a lot of work being done in explainability of what these, ML and AI systems are doing. And so that's really, really useful for the intents of, if we couple a human with some type of assisted, machine learning assisted, data-driven fusion thing, that we actually understand how it's actually coming to what it thinks it's recommending. So great question, and in an area that's really ripe for future development. And maybe somebody in the Hertz community will pick up that charge. So thank you so much.